I'm Niki Castle. I work at a company called Appboy, and I'm going to give a talk that's a little different than maybe the ones that you've been to, certainly the ones that I've been to so far, in that I'm not actually going to talk so much about a database and how it works, but more about some of the interesting use cases that I've run into, dealt with in the process of building what turns out to be a state machine, using MongoDB with Redis for a bunch of backup help. So first, just to give you a little bit of background into why we want to do the thing that we're trying to do and what our motivations are, I'm going to give you a little bit of background on the company. We don't build apps. My favorite line actually at career fairs is, yeah, I know I'm not a boy. Also, we don't build apps. So, 3 ways that we could describe ourselves is that we call ourselves a CRM platform. It stands for Customer Relationship Management. I'm not entirely sure how common a term that is. Specifically, we're a marketing CRM platform, so we provide this platform for our customers, which are brands and apps, to communicate with their end users. We also, as a result, send a whole lot of messages and try to provide analytics on a whole lot of events coming in, maybe like 2 billion a day right now that we're processing. So what this means is that some of our very fundamental goals, at least for the message sending part, is that we want to try really hard to send a message whenever possible. We never want to send more than one message, and we definitely never want to send the wrong message. So any message that our customer is not eligible for, our end user is not eligible for, we had better not be sending. It's very important. We get in a lot of trouble. We don't want that. So when I say state machine, I'm talking about a slightly specialized form of one. This is a graph that I made that sort of follows the flow of a dumb graph joke that you might make with a flowchart. The specific things that I want to call out is that our state machine has an entry point, or maybe multiple entry points. So the question is the entry point. There's nowhere that you go to the question from. You just enter there. And it has points where you drop out and you can't get anywhere from there. So both the punchline and the short circuit in this place are places where our users would end. And the specific state machine that we're talking about is called Canvas. That's what the marketing team decided to call it. I actually like the name for the most part. The only thing that I didn't like is that we already had campaigns as a concept, so everywhere that I wanted to do CID, it was already taken. So we're going to go over just a little bit of the motivation for Canvas, a couple of examples of what it actually looks like to make sure that we're all on the same page, the constraints that we care about, and then what the user state that is relevant to this talk we're tracking. So first of all, let's go through a side-by-side of what linking 2 steps, 2 campaigns together looks like before and after Canvas. So before Canvas, we have a campaign wizard. It's 5 steps. You set up a message. You set up a schedule. You set up audience filters. So you can say like, oh, I want people to receive this only if they are 35 and over. You add conversion events, and then we have a confirm step where you review everything and make sure that it's right. So you can go through this twice or once per step. And then you would set the second campaign's a couple of special attributes on there to ensure that it was linked together with the first campaign. So first you would make sure that the second campaign doesn't include anybody who hasn't received the first campaign, because otherwise they wouldn't be flowing from the first campaign to the second campaign. They'd just be receiving the second campaign. You make sure that your time windows are right. So you want maybe like a week between these 2 sends. Say that I'm doing an onboarding flow and I send my user a message when they sign up, and then a week later I want to see if they're still using the service. So I want to make sure that those are set up in a way that makes everything work and mostly hope for the best. The one thing you can do, because our customers also want to be able to see how all of these are performing in comparison to each other, is that we offer a tagging or labeling feature where you can add a label and then search by that in the grid. So you can at least get all of them on the same page, but you just see the campaign names there. If you actually want to see the analytics and compare them against each other and see how they might be filtering down, you have to open them up and run a whole bunch of stuff yourself. After you make a canvas, you build 2 steps, which we'll see on, I think, the next slide, but maybe the one after that. You link them together by clicking the bottom of one and dragging and clicking the top of the other. And we'll handle all of the eligibility constraints that you were worried about with the audience and time windows for you. And then you can see this on the analytics page, how users are flowing through this journey. So this is why our customers want it. This is maybe not as interesting to you, but just as sort of the motivation for why this is something that we felt it was really necessary that we build. Yeah, great. This is what it looks like. So here's like just an example of two steps that flow into each other. I say the base case, it's not quite because I've included a few of the different, do I have a mouse? I do have a mouse. I have a few of the different constraints or features that we'll be talking about. So this simple base case is that the first thing that I have to do as a user is perform a trigger event, and I've called that trigger event beat level. So if I perform the event beat level within the time window of 1 day, then I wait 1 hour, I don't check any additional audience options, and then I send an email. And then I move on to the next step in the journey. After 1 hour, if my language is set to English, I will receive a follow-up push. What this actually looks like in practice is that our customers do more complex things with especially branching. And instead of having one welcome message that's for English speakers, I might have a message for English speakers, a message for German speakers, a message for Chinese speakers, a message for for Russian speakers, etc. And those might all be set up to go off at the same time, but I'd be able to send out these different messages to different people. So the next question that we maybe want to think about is how we know at this point, as soon as we receive this message, what our user's language is. So our user probably has a language here. Maybe they don't, maybe they're new, maybe they haven't signed up yet. That's the most likely case for why it might change in between, but it might change in between. And so just keep that in mind, that the time that we actually want to check what the user's language is when we're sending the message, not when we're sending the previous message. So some of the constraints that we're looking at here are for our state tracking. We care that this message is sent at the right time that we've set it up for. We care that the user has all of the correct attributes, that they fit into the audience that we've assigned this step to be sent to, that they've performed any necessary trigger actions to receive the step, and that they haven't performed, we didn't show this, but they haven't performed any exception events that would cause them not to receive the steps. So maybe if I'm sending an abandoned cart flow, I want to send messages until you purchase. You've probably all seen this on some kind of e-commerce site. If you put something in your cart and then you leave, they're probably going to send you an email. Often they give you a discount. It's a good tip if you haven't seen that before. But if I buy something in between that, I don't really want to send that message. Our customers don't want us to send that message on their behalf. So we want to make sure that we don't do that. Getting a little bit more technical, we want to limit ourselves to one Mongo write to commit our user's state change. So at the point where they actually transfer state, that is, they receive the following message, that's when we want to write. We want to avoid making any other writes to Mongo in the process because we're in the critical flow of the sending journey at that point, and we want to avoid the overhead of that time if possible. We definitely don't want to write halfway completed states to the user profile because we want this to be granular actual straight transitions. And finally, the fact that I've alluded to before, there's a delay between when we want to execute these state changes. We don't actually want to look at the language of the user when we're getting ready to enqueue the job or whatever, right? At the end of the last step, we want to look at that language when we're sending the current message. So our user state, or the pieces of it that actually matter to us here, are that we're going to store for each user a map from the combination of the journey ID, so whatever flow that our customer has set up, and the entry timestamp, so the time that the customer entered this time. So if you take an example where a user is playing music, I might play one song, and some app might want to send me a follow-up saying oh, you played this song, you might also like to look into this, and send in something a week later that is also saying here are some more songs in that genre that you liked. But maybe while I'm in that week waiting period, I might enter this again, and so that's the reason that we have to be sure about the timestamp so that we can exist at multiple points in this journey. Is that reasonable? Okay. So let's talk about how we actually do this branching. In theory, it's not that hard. It's pretty straightforward. We want the user to only go down one branch. So what that means is that we enqueue all of the jobs for the future. And so we actually use Sidekick to do this. So this is also Redis, but not so directly my doing. So we try to send all of them. We enqueue all these jobs for 1 week later. They'll run 1 week later. And as soon as one of them succeeds, we just want to cancel all the other ones. But as anyone who has worked with Sidekick may know, it's not actually very easy to cancel jobs because of the way that they're stored. You can't really access them again. So the way that we need to get to that is somehow when the job runs, that's when we'll be able to say, oh, like, actually, sorry, don't want you anymore, just fail out, die, bye. So the things that we need are that way to cancel steps. We need to guarantee for our customers that they're never going to go down more than one branch. What is the word? The user is like in a state of quantum superposition for any physics nerds out there, and we want them to coalesce into one node. We don't want them to continue in multiple states and like start receiving all of these branches and get every single message that our customers set up that anyone could possibly ever receive from this campaign, because then they would be flooded and they would complain on Twitter and our customer would come to us and say, what the hell? And we would like very much to guarantee that if this end user is eligible to receive anything, we're going to send it to them. But we recognize that there are some places where we might be able to be a little bit flexible on this, because it's not as important to us as long as we can minimize the cases where a user winds up not receiving anything. Okay, who's seen one of these before? Remember these? I know that like they've gotten better, and now the correct thing to do is the ulock with the key. But I love these. Anybody remember how they work? Maybe some small nods. So each of these numbers corresponds to a gap. The wheel is solid throughout the rest of it, but there is a gap at the right number that you've set for your code. And when you line them all up between the arrows, the result is that there's a gap straight through, and that's the only way that the key can pull out, because otherwise they are all held in place by any one of those is enough to restrict you from being able to open the lock. So if you go back to the state considerations that we talked about before, these numbers are sort of equivalent to our time, our user attributes, the actions that we've performed, the actions that we haven't performed. Everything has to be right before we can actually send the message or pull out the key. So if we go back and look at our example again, that means that we're enqueuing all of these messages, which is like sort of a secret. But at the point that they run, that handles the time and the event for us. And the two that we still have to worry about, the actions performed, the two that we still have to worry about are the user attributes, which is that audience options here, and the actions not performed, so the exception events, which we're not covering too heavily. So once this job runs, we've guaranteed those things. We still have to make sure that the other things are okay and that we can actually go ahead and send the job and pull the trigger. So the way that we want to do this is that we're going to use Redis to grab a lock. Because all of these jobs have access to that. They all know which step they're coming from because they're all sort of the same potential state for the user. So because each one represents, as it says, a unique instance of a user in a journey, these are the things that we care about for our key. So the key has to take in the journey ID, the user ID, and the entry ID. We actually use a timestamp, but anything that uniquely identified the instance of the user in the journey would be adequate. And then because it's Redis and it's a key value store and we don't have to store just true, we store the branch ID as the value. This is actually only for debugging so that when a step runs and sees that this lock is held, we're able to say, oh, it's held by this step, and have that available to us if anything goes wrong. Which so far, knock on wood, it hasn't, I hope. So we acquire the lock, we do all of our sending, and then we release it, and any other steps can run. At this point, if they do run, they won't be eligible because we will have moved on down the journey. So the way that this actually looks is that we start at this top node, the right step, and we check to see, so this is the check, are we eligible for this step right now? Is this one of our next steps on the user profile, which we do read from Mongo. So if it's not, then we cancel out. I should call out here that we don't actually retry this right now. We go ahead and completely fail. It's for performance reasons and may change in the future, but in case anybody's expecting a retry, we don't do it at the moment. Then the next thing that we try, assuming that this was successful, is to see if the lock was acquired. So we try to grab that lock, and either it returns yes, and we're good, or it returns no. So if it returns no, again, we just cancel out. If it returns yes, we're like, great, let's try to send. So red just means that we're locked, not that anything's wrong. The next thing that we need to check as part of the sending process is that the user is in the audience. And so if they're not, again, we cancel out and then we release the lock. If they are, we continue. We go through the entire sending process that all happens on that arrow because it's super fast, because we're good at that. And then we finish up. We are committing our state. We update the user profile. And once that's done, the next time that we check this right step for any other step, it won't be eligible, so we can safely release the lock. Anybody see any problems with this? I didn't the first time. It turns out that doing that attribute check for our specific use case especially, oh, that's annoying. Okay, for our specific use case especially, we have these 4 steps that are all going to send at the same time or attempt to send at the same time. And we can pretty much guarantee that our user will only be eligible for one of them at that time. So the chance is 25% that the first one we try to send is the right step, 75% that it's not. And because they're all sending at the same time, the chance that the correct step tries to send while that lock is still being held incorrectly is like pretty high. In practice, we ran into it like 20 or 30% of the time, I think. So the way that we decided to get around this was to eat the cost of an additional Mongo read, which was not actually terribly expensive. It was like 1 millisecond with caching, to check that the user had the right attributes before attempting to acquire the lock. And we still have another check later down the chain to make sure that we're as close to the actual send time as possible, but the likelihood that it changes between those 2 points is now like drastically reduced. So the time between acquiring the lock and releasing the lock is exactly the same, but we've removed this chance that we're incorrectly acquiring the lock entirely now, which it turns out is way better for our customers because that's a very valid use case, even if we would like them to send them a different time. No, that's actually a really good use case. Okay, so that's branching and all of the difficulties we had with it, some of the difficulties we had with it. Another way that we used Redis to solve a complex issue with Canvas is by doing some batching. And the reason that we had to do that is that when you have large customers using your product, the number of jobs that we're queuing by doing all of these branches at the same time is equal to the number of users in the canvas at that time times the number of branches that they could potentially be going down. So if you have, say, 10 million users that a canvas is sending to, and that branches out to 11 branches, you wind up with 110 million jobs all enqueued for exactly the same time, which Sidekick chokes on a little bit because it's trying to pull them, and like the workers start conflicting, and then also like only one of those is still ever going to send, so they still have to like run through all of them. And we looked at a couple ways that we could potentially get around this. One of them was to do one job per user per many branches. So in this case, with 11 branches, we would enqueue one job. That job would have the responsibility of figuring out which of the next steps the user should receive, which gives us the additional advantage of actually being able to guarantee that our user is going to receive a step, which gets us that 100% always going to send something if possible, up to like an actual guarantee. The other thing that we considered is one job per branch per many users, which means that for each branch, we figure out a way to enqueue one job for a group of users that are all set to receive it at the same time, which is highly likely when you have that many users going through, and enqueue that instead. So in this case, many is like order of magnitude tends to be around 10. In practice, you could totally get up to like, well, we don't actually limit it. So you can get up to a very large number, but our customers still have to deal with this on their like MacBook 13-inch, 11-inch, whatever. And in practice, it turns out that like 4 to 5 is common. 11 happens clearly, but not as often. And in terms of here, we'll call many approximately equal to 100. It's probably like between 100 and 1,000 that is like a very reasonable number of users to attempt to batch that we're going to run into frequently. Like actually be processing them to receive at the same time. But 100 is like a reasonable lower bound that also shows that it's definitely an order of magnitude faster than this one. So we picked that to start with. We're still considering the other one at some point in the future, but this actually was highly effective, so we haven't done it yet. And the way that we went about this is that, so previously, we process events that come into us through our SDKs or wherever against our users, and we do a whole bunch of things with them. This is only one of them, but we see if there's anything that they should be triggering, and we enqueue a dispatch job for that user for that desired send time. So the way that this works, if you have 1 million users, you have 1 million jobs per branch, or like per anything that they're enqueuing. The way that we're doing it now, we process the event for the user. We add the user to a Redis set under the key of the branch ID and the timestamp that they should be sent at. So that's ensuring that we're still going to send to users at the right time. We still want these like high real-time guarantees. So we don't want to like delay that at all. We enqueue a batch job for something like 30 seconds in the future. Again, we're only doing this if we're actually trying to send in the future. If we're trying to send immediately or less than whatever that wait time would be, we go ahead and send. We do this using another lock key just to ensure that we're only running one of those batch jobs at a time. And that batch job, when it runs, the first thing that it does is release that lock key so that if we process another user, we can enqueue another job and be sure that we won't miss anything. It also, at the end, checks to see if the queue is like large and enqueues more of itself to ensure that we don't run into any issues with buffer overflow if this machine is just processing a little bit more slowly. The batch job runs. It pulls the users off the Redis set. We picked 200 for now. It's been effective. During these large sends, we do get up to that number pretty easily. So it's in that order of magnitude. And we enqueue one dispatch job for all of those users for that desired send time. And it's not the same dispatch job, but it is analogous. It actually loops over the users and does all of the same things and also manages to batch the Mongo read that we do to check the user's eligibility ahead of time, which gains us a little bit more efficiency there as well. And now we've brought that 1 million users down from 1 million jobs per branch to 5,000 jobs per branch, which is a whole lot more manageable. So, okay, these are like a couple of the things that we've dealt with and how we solved them. And I am happy to take any questions either now or later. Also, we're hiring, like everybody else here. Cool. What's up? Huh? Yes. As a company or for this specific project? Yes. Yeah, it's certainly worth considering. We use Redis in a ton of places right now, like very heavily for these and many other use cases. So it's not super clear whether the effort to replace it for all of those things would be worth it at this point, but it's certainly something that would come in handy for the future for like maybe not having to deal with as many things at one time. Yeah. I'm going to ask a really dumb question. What do you mean by execution context? I don't know all the words. Rails, mostly. Rails, mostly. Not entirely. We have added some, so the sender jobs have actually recently moved to Go, and we're transferring over to that. And we're also adding an easier framework for adding microservices at the moment, but still mostly Rails. She just gave me the 1-minute warning, so you guys can all go too.